What is the strangest thing humans have ever found on the moon? It wasn't aliens, not secret bases, but something that shouldn't have existed at all. And with the arrival of our new crewed lunar landers, this discovery is becoming more important than ever. More than 50 years have passed since Apollo astronauts last set foot on the moon. Half a century of silence. No human footprints have touched that surface again. But we did send dozens of robotic probes afterward. Some landed successfully, some orbited, and some were deliberately crashed into the moon just to see what they might reveal. Overall, the moon is the most explored object beyond Earth. Yet even after decades of research, it remains full of mysteries, from how it stores heat, to how it conducts electricity, to the strange behavior of lunar soil. There is still so much we don't understand. That's the universe for you. The deeper we study it, the more questions we find. For example, before we had actual lunar soil, we were full of expectations. But once lunar samples were brought back, strange discoveries began one after another. Chemical traces that shouldn't exist. And for the next few decades, these clues tortured scientists. You might think a scientific discovery instantly changes everything, but real science moves slowly, painfully slowly. Sometimes everyone notices something, but no one believes it. To understand this mystery, we need to go back to 1976. That year, the Soviet Union launched an unmanned probe to the moon, Luna 24. It was their final mission to dig and bring lunar soil back to Earth. At the time, nobody paid much attention to it. It wasn't the first and it wasn't a big mission. But quietly, it did something huge. It drilled nearly 2 meters beneath the lunar surface and extracted a narrow column of lunar soil. The sample weighed only about 170 grams, about the size of a baseball. Not much, but inside that thin tube of dust, something strange appeared, a trace of water. About 0.1% of the sample contained water, and the deeper researchers analyzed it, the more water they found. It should have been a major discovery, but instead, scientists dismissed it. They assumed the sample was contaminated, maybe from the lander, maybe from Earth's lab equipment. Because the textbooks were clear, the moon is dry, it cannot have water. And this wasn't the first time. Apollo samples from the United States also showed hydrogen signals, but those were also dismissed as contamination. So these clues that should have shaken the world, were quietly buried in the corners of research papers, and no one talked about them again. Not until the turn of the century did people start to wonder, had we missed something important? But by the time we were ready to revisit the mystery, the moon was ready to throw us even bigger problems. If you were dropped near certain craters at the lunar poles, you'd see something almost unnatural. Not because something is there, but because nothing is. No light, just shadows that have stayed frozen for billions of years. These places are called permanently shadowed regions. Why do they exist? Because the moon stands unusually upright with a tilt of only about 1.5 degrees. So when sunlight reaches the poles, it skims across the surface almost horizontally, and crater walls are tall and steep. Sunlight can't reach the bottom at all, which means some regions may not have seen a single ray of light in the entire history of the solar system. They are not just dark, they are unimaginably cold. The coldest spots drop below minus 240 degrees Celsius, colder than distant Pluto. These may be the coldest places in the entire solar system. Back in the 1990s, scientists began to wonder, if comets or asteroids once struck the moon, could they have delivered water? And could that water vapor have drifted into these shadowed pits, frozen in place and never escaped? This idea exploded in popularity because it meant the moon might not be a dead rock. It might be a resource depot, a future gas station for deep space missions. From then on, all eyes turned to the lunar poles. Looking from Earth was no longer enough. We had to get up close. But the problem was, the most promising locations were also the hardest to reach. The terrain is brutal, and there's no sunlight to power solar panels. But the potential reward was too tempting. What if there really was ice? So wave after wave of lunar missions began, all chasing one goal: find hard evidence. But just when things seemed straightforward, the story took another strange turn. If scientists suspected ice, the next step seemed obvious: send a probe to check. But landing directly was too dangerous, so the first waves of missions observed from orbit instead. The first was Clementine, launched by NASA in 1994. It wasn't designed to look for water. Its main mission was to map most of the moon. But it confirmed one thing: the South Pole truly had massive, permanently shadowed craters. However, Clementine carried no instruments capable of detecting ice. Then came 1998, when NASA launched the Lunar Prospector. This one was built to search for water. Using a special neutron spectrometer, it detected large amounts of hydrogen at the poles, especially inside the shadowed regions. Scientists were thrilled. Theoretical estimates suggested millions, even billions of tons of ice. Not a puddle, but a discovery capable of reshaping the future of space exploration. But then came the problem. Finding hydrogen does not guarantee it's water. Hydrogen might be part of hydroxyl or trapped inside minerals. The instrument couldn't tell the difference. It could only say hydrogen is here, but not whether that hydrogen belonged to ice. So what was it really? Even if it was water, orbiting spacecraft couldn't see it directly. So it still wasn't hard evidence. Once again, lunar science hit a frustrating wall. We had clues, but no confirmation. It was like the moon whispering, "I have a treasure, but I won't tell you what it is." So scientists thought, if we can't see it from orbit, then let's do something simpler. Let's crash into it. Yes, you heard that right. Crash into the moon. The logic was simple. If ice is hidden at the bottom of a crater and sunlight can't reach it, then we smash something into the crater, throw debris into sunlight, and analyze what comes up. Brutal, but effective. The first attempt came from the Lunar Prospector in 1999. After completing its mapping mission, it deliberately crashed near the lunar South Pole. But unfortunately, the experiment failed. No water was detected. The results were inconclusive. Some said the impact angle was wrong. Others said it hit too gently. 10 years later, in 2009, NASA tried again, with a mission that would change everything: LCROSS. This time, NASA played it smart. They used the empty rocket booster that carried LCROSS into space as a giant projectile. The rocket slammed into a crater called Cabeus near the South Pole. Minutes later, the LCROSS spacecraft flew directly through the debris plume and analyzed it in real time. This time it worked. Its instruments detected water vapor in the plume. Not hints, not speculation. Real measurable water, and not just water, but methane, ammonia, and other compounds. For the first time in history, humanity had touched water on the moon. News headlines exploded worldwide. Scientists celebrated with champagne. It felt like a decades-long mystery had finally been solved. But very quickly, another problem appeared. We had confirmed water, but how much was there? Was it solid ice? Was it mixed with soil like a slushy? And most importantly, could it actually be mined? LCROSS gave us the answer we desperately needed, but it also destroyed itself in the process. It could tell us water existed at that exact point, but it couldn't tell us the moon's whole story. Up to this point, everyone assumed something simple. If the moon had water, it must be hiding in the coldest, darkest shadows, places sunlight never reaches, like a natural freezer preserving ice for billions of years. The logic was flawless, but the moon loves making things difficult. Orbital spacecraft, like NASA's Lunar Reconnaissance Orbiter, launched in 2009, and India's Chandrayaan-1 began detecting faint signs of water molecules outside the shadowed craters. This shocked everyone. Finding water where sunlight hits the surface? Those areas heat up to over 100 degrees Celsius during the day. Any water should have evaporated instantly, but the mystery only deepened. Scientists noticed the signals weren't constant. They followed a daily cycle. At noon, when sunlight was strongest and the ground was hottest, the water signal weakened or vanished entirely. By evening, when temperatures dropped, the signal returned. What was happening? Was the moon sweating? Sweating in the day, absorbing again at night. This defied everything we understood. The moon has no atmosphere, no air pressure, no weather, no clouds, no water cycle. On Earth, water evaporates, condenses, forms clouds. But on the airless moon, where would a cycle even come from? This instantly became one of the moon's greatest modern mysteries. So where was this water coming from? Scientists proposed a few possibilities. One idea: micrometeorites deliver it. Every day, countless dust-sized meteoroids hit the moon, some carrying tiny amounts of water. Or they strike lunar minerals and release the water locked inside. Another idea is even more surprising. The sun might be creating the water. The solar wind, full of charged hydrogen ions, hits oxygen in the lunar soil and synthesizes water molecules on the surface. No matter the source, this discovery changed everything, because it meant we might not need to rely only on the polar craters. Maybe the entire moon is coated with a thin layer of water if we have the technology to collect it. Suddenly, the possible locations for future lunar bases expanded dramatically. This intriguing possibility sparked the next generation of lunar missions. And in 2023, Indian scientists stepped onto the stage. Chandrayaan-3's lander and rover were sent straight toward the South Pole, the region believed to hold the highest concentration of lunar ice. It became the first spacecraft in human history to land there. Everyone waited, eyes wide, expecting the Pragyan rover to send back news of ice. The rover deployed its instruments, lasers, X-rays, spectrometers, analyzing every bit of soil it touched. And the results? It found aluminum, iron, calcium, sulfur, but no hydrogen. And without hydrogen, there is no water. The world was stunned. Where was the water we expected? The maps were clear. Something should have been there. Had our theories been wrong this whole time? Or was the water simply buried too deep for the rover's tiny scoop to reach? Before we could find answers, the 14-day lunar night arrived. Temperatures plunged below minus 100 degrees Celsius. Chandrayaan-3 didn't survive the cold. It fell into permanent sleep, but before it died, it left behind a critical clue. Using a temperature probe, it measured the lunar soil. The surface, heated by the sun, was scorching, over 60 degrees Celsius, but just 8 centimeters below. Temperatures dropped to minus 10 degrees Celsius, an enormous temperature difference. What did that mean? It meant the uppermost layer of lunar soil acts like thick insulation, blocking external heat from penetrating downward, which perfectly explains something important. Why the rover found no water? Because the ice might be hiding just a few centimeters below, close enough to exist, but too deep for the rover's tools to reach. So the problem is no longer whether the moon is dry, but whether our tools are sharp enough. We may not need better theories. We simply need a stronger drill. If this is true, then the next lunar lander won't need to travel farther or see more clearly. It will simply need a better drill. For decades, the search for lunar water was treated as scientific curiosity, a way to understand the moon's history, geology, and how water moves through the solar system. But today, water on the moon means something far more direct, a stepping stone for humanity's push into deep space, and the foundation for future space bases. If we can find usable lunar water, enough to extract, purify, and store, then it unlocks everything else. Lunar water makes long-term moon missions possible. Water is heavy and expensive to launch from Earth. Every liter we send is like shipping liquid gold. But if astronauts can get water locally, they won't need constant resupply missions from Earth. They can drink it, cook with it, clean with it, and cool equipment with it. Water can be split into hydrogen and oxygen, the perfect rocket fuel. Many modern rockets use this exact combination. If we can extract ice and convert it into propellant, the moon becomes more than a destination. It becomes a refueling station. From there, spacecraft could launch toward Mars, asteroids, or even deeper into the solar system. This completely changes mission planning, because right now, every mission must carry all its own fuel from the very beginning. Launching from the moon is far easier. Its gravity is only 1/6 of Earth's. Less gravity means less fuel, lower cost, and bigger missions. Local water changes how we build future lunar habitats. Water enables closed-loop life support systems, recycling waste into usable resources. It even makes growing food on the moon possible. Some plants can grow in lunar soil under controlled conditions, but they still need water. If enough water is found, future habitats won't rely entirely on resupply, supply drops, or hydroponic imports from Earth. Water could define humanity's entire deep space future. Its importance is enormous, but we still don't know how much usable water the moon truly holds, or how difficult it will be to extract it. All plans for lunar fuel depots and deep space launches depend on one thing: can we get the water? Which brings us to the final question. Despite all the missions, data, and optimism, we still do not have a clear path forward. Every time we think we understand the moon, it throws something new at us: a contradictory reading, a missing signal, an unexpected result. And this pattern repeats endlessly. From orbit, we detect strong hydrogen signals. But on the ground, landers find no hydrogen at all. We find water vapor and impact plumes, yet no frost, no ice sheets, no visible deposits. Even in craters that have never seen sunlight, places cold enough to preserve ice for billions of years, high-resolution cameras still find nothing that clearly looks like ice. Instead, we keep getting ambiguity. Shallow probes find nothing. Spectrometers detect water that vanishes in daylight. Rovers cross craters expected to be packed with ice, only to find more dust. Even new technologies like shadow cameras, designed to image the darkest places on the moon, still haven't revealed the bright, reflective patches scientists hope for. A troubling possibility emerges. What if we've been wrong about how the moon stores water? What if our models need rewriting? Or worse, what if the water is there, but spread so thin, buried so deep, or chemically bound so tightly to the soil that we simply aren't ready to extract it yet? Optimists offer another explanation. Maybe our tools, though precise, just aren't good enough yet. Orbiters are like eyes in the sky. They see everything, but touch nothing. Landers and rovers are like fingertips. They can touch the ground, but not dig deep. All our attempts feel like scratching an itch through a thick glove. We're close, but not close enough. Spectrometers send back data full of riddles. Hydrogen is here, but not where it came from. The ground is bright, but is it ice or a shiny mineral? Still, giving up is not in humanity's vocabulary. The deeper the mystery, the more curious we become. New missions are already in the queue. Stronger landers are under construction, and all eyes remain locked on that place. The place we believe hides a treasure. The next mission may carry a far more advanced lunar Luoyang shovel, a deeper drill, a smarter extraction system, no more shallow tests. This time, it aims to pierce through the moon's thickest layer of mystery, to reach beneath that insulating lunar soil and lift a handful of cold, solid ice. Of course, the moon may play another trick on us. We may find even more unanswered questions. But when our Loyang shovel finally raises that first piece of real lunar ice, a new era, bigger than Apollo, will begin. And when that moment comes, the blue planet beneath our feet will no longer be the cradle of civilization, but the harbor from which we launch into the ocean of stars.